Should have recorded all that. But. All right, well, welcome to class on Valentine's Day. I just remembered, I knew it was Valentine's Day, but I just remembered when I saw the Google Doodle there. This is a class that I've taught several times before. It seems like every year I teach it, I'm like, oh, should have moved cost distance modeling down below terrain and surface modeling. So we do, it really doesn't matter the order, but we do some, we've already talked about slope a few times, so it'd be nice to talk about terrain derivatives here, and we're gonna do that again in today's lab, but it's not super important. Also, terrain and surface modeling builds a little bit more off of neighborhood and zonal operations than today's topic. Cost surface, cost distance modeling. But that is today's topic. All right, y'all can see everything, right, on the coast? Yeah. Cool. So, great. We'll begin. I'm gonna make it bigger for the coast. I think if I tell it, so by default, I get this screen. I get like a preview of the next slide and this slide, where you guys get that. But if I change it to a different setting, can you all see everybody can see my mouse, right? Yeah, that works. So I can point at things. Supposedly, we're just waiting for this awesome system to get hooked up where I can even draw and do great things. But so we're going to talk about finding distance today, and this builds actually a little off of the proximity analysis that we talked about the first week, and it also builds off of the concepts that you may or may not have done. It doesn't really matter if you've learned it or not, but it's kind of in a way similar to finding the best route through a vector network or a network graph, as probably most mathematicians would refer to it as. So we're going to talk about that. So just as a review, if we create a distance raster or a distance grid, whatever we want to call it, one of the inputs is the source. Okay? And so what is the output? In the raster output, what do the values it's called the Euclidean distance operation in ArcGIS. What do the values represent in each cell in a Euclidean distance operation? What's that? Yeah, they represent not time, but just distance. Yeah, just Euclidean distance. So they'd be a good surrogate for time if you were to just travel back to the source and there were no impediments, there's nothing to block your path back to the source. Now, they're the fastest path back to the source. So if you have a polygon source or you have multiple points or multiple polygons, then just with the output raster, all you know is the fastest distance back. You don't necessarily know which one. And so commonly, most GIS software packages also allow you to specify another optional output that specifies both either the direction or the unit ID for the particular source data set that it's traveling back to. So those are both analogies that you'll find in what we're going to talk about today. I have to press enter. Okay, making sure I'm on the right side. All right, so again, this is just review. Every distance is just the straight line distance calculated from the center of the cell back to the source. So we showed this math previously, but basically what that's saying is that if you're on a diagonal, you have to remember to take that into account. So today, we're going to talk about cost distance. Cost distance is an extension of finding straight line distance. So one way to think about straight line distance is that it is cost distance, with only one factor considered, and that's the flight time or the straight line distance back. So how is cost distance different? Well, basically, costs are added to the equation. So how are costs added to the equation? Well, that's what we're going to talk about today. So in order to do this, we have to establish a GIS layer depicting the minimum cost of reaching cells in a layer from one or more source cells. So similar to the just a straight line distance, cost does require that there is a source. In other words, the cost to something. So that's the output. The result is going to be a grid where the cost to get back to the source is established. So what are the required inputs to get such a data set? Well, we still need a source layer, which is the second one, this one here. Okay, it can still be a single source, or it can be multiple sources. The new layer, the second input required to cost distance modeling, is a friction or initial cost surface layer. And this is the surface that's kind of similar to, in a vector data set, if you were to pick a field that represented the cost to traverse that vector. Now we're going to have a single raster that represents the cost to traverse a single raster cell. This is the workflow, all right? The workflow of doing a cost distance application. There's a test question that has you do this. There are a couple of different outputs, just as there are with the Euclidean distance. The primary output is simply the cost distance. So we have our sources as input, but now we also have another data set that represents the cost to traverse every cell. And these two data sets are the input to the cost distance algorithm. The cost distance algorithm, when I say it's complex, what I mean is that it doesn't fit really neatly into the kind of categories that I talked about before, which were local, focal, zonal. It basically, just like the vector version, it has to try a bunch of different things. And so it's a recursive algorithm that tries different paths and converges on the correct path without having to try every single possible combination. So anyway, that cost distance algorithm runs, and it chooses, based on the costs and the sources, the primary output is a cost distance thing. So what do the values in every single cell represent in this cost distance raster? I've stated it, but I'm asking that as a question so that one of you all will restate it.
The minimum cost of reaching the cell?
The minimum cost to travel
To the source.
to the source, yes. To travel. One of the things about the way that raster cost distance modeling is implemented in almost all GIS softwares that I know of is that it is actually anisotropic, meaning that it is the same in either direction. So the traveling back to the source or from the source to a particular cell, it's the same distance. But yes, the value of every cell represents the cost to either travel back to the source, or you could think of it as traveling from the source to this location. And optionally, you can output cost direction, which will tell you for every cell, it will tell you the direction that you have to travel to follow that minimum cost back to the cell, the initial, the source, or vice versa. And then oftentimes there's a second tool that is run that will actually use the cost direction and the cost distance, as well as any destinations that you specify, and create a least cost path. In other words, it's like if you've used Network Analyst in our GIS, it is very similar to finding the fastest route from point A to point B. And even if you haven't, you've all done it on like Google Maps or whatever your favorite mapping application is. When you type in, I want to travel from Hattiesburg to Detroit by car. I don't know why you'd want to do that, but you could travel up, through Nashville. It would show you the fastest route to that location. That's using vector GIS data, in other words, lines. But you can kind of think about the raster as each raster cell. You could think about each raster cell as being like a star, where you have a vector going diagonally across one direction, diagonally across another direction, and then plus through either way. If every single raster cell looked like that, and the cost was assigned then to all those signs, those different lines, you would get the same answer. That's what your least cost path would be. But it's a raster where it's just the output here in the least cost path raster is either one, meaning that it it traveled through that, or no data, meaning that it didn't choose that as the least cost path. We'll show that as an example here in a second. One more thing that we should talk about here is our friction surface. Our friction surface, that's the surface where the cell values represent the cost per unit travel distance for crossing each cell. Okay. So it assumes the cost for moving in any direction is constant. Wait a second, is that? Because I said anisotropic. Not. Anyway, raster assumes that traveling across the cell in any direction is the same cost. So it actually works in a lot of cases just fine, but there are cases where it kind of breaks down. Can anybody think of a situation where it might cost, what's that? Yeah, up and down rivers. Now rivers aren't typically modeled in raster, so they would be great to model in a vector data format, and the vector model does allow to have different costs for traveling up and down. But yeah, up and down the mountainside. So a lot of people try to, well, not a lot of people try. A lot of people successfully model that as what? How could you make it more expensive to go up a mountainside? Yeah, the slope. So if you assume that you're going to start towards the bottom of a hill, and you want to say what's the fastest way to get to the top of the hill, then you can just use slope as a cost. The problem is that if you don't know if you're going to start at the bottom or the top, and you use slope as a cost, what happens then if you are at the top of the hill and you want to model getting down to the bottom of the hill and you use slope as a cost? You've just said that it costs more to go down the hill faster, basically. And it might, like, my knees are getting bad, you know. Yeah, it doesn't matter. So there may be a good reason. Also, when you're like talking about like building something, like building a road, it often doesn't really matter if it's a slope that's going up or down. It's a similar cost. So there are a lot of applications where it doesn't matter, but there are some where it does. Like if you just wanted to find the quickest way to get down, and you knew you could travel faster downhill than up, it would definitely cause an issue. That's what I'm trying to say. And you'll find even more issues when you're trying to model the flow of something, particularly through water, like Forrest said, but more like on a lake or an ocean, it'd be even larger. So, you know, the current going one direction is a big deal compared to the current going in another direction, like if you're traveling in a boat or whatnot. So those are some examples where it's not the right choice. This is something that's been in most GIS systems for a long, long time. Cost surface modeling has probably been in GIS systems for 30 years now, and I'm still waiting for somebody to implement a raster network model. I don't think it would be that hard. I guess the way I think about it is you might have to have like 8 different layers, or maybe just 2 layers, but somehow you would have to model the different costs associated with traveling through in different layers.
Dr. Ray, what you mean by traveling? Are you talking about a mode of transportation to accomplish that type of movement? And with value costs like a car, boat, or plane, train? Is this a visual thing?
No, so yeah, I mean, I guess I kind of went off on a 2 or 3 minute tangent there at the end, but I think your question just refers to the friction surface itself. It doesn't really matter what the mode of transportation is. It's the cost to travel through that for whatever mode of transportation you want to model. So if you're modeling walking, then it's the cost. And what is cost? Cost can represent time. So it's the cost in time to walk through that cell. It could represent the cost in travel time. It probably wouldn't be a car. You typically wouldn't use, because cars have to travel on roads, right? So you could say, well, like, what if I was driving a tank through the woods, and I know the tank could travel through the woods, but it would take a little bit longer, and so I would increase the cost to drive a tank through the woods and kind of estimate the extra costs associated with having to navigate around huge trees that my tank just couldn't drive over.
Well, how about the destructive cost of moving through a particular location? Would you put that in, like in Germany, you go through, check through millions of dollars on trees?
Yeah, so cost doesn't have to be time. That's a great point. And I will show an example. The slides are at the end of the lecture that we did when I was a graduate student. And that was, what if we wanted to build a new road or a new railroad? The railroad is the example here. I've showed the example in several of my other courses, so you might have seen it. But the cost could be the real cost associated with, like cost in terms of dollars, associated with paving and grading and anything associated with modifying a particular cell and turning it into a railroad rather than a regular, than an open piece of ground. Cost of acquiring the land. So the cost could be real costs. In fact, that's one of the biggest applications as well. Like, it's not all about planning a walking path or planning in a war, planning a tank driving through the countryside. It is also about finding a new road, finding a new path through a certain area. I've also seen other applications where people use it to model the behavior of an animal and say, okay, well, if an animal was going to go from here to here, which path would they most likely take? And so there, the costs are a little bit more abstract, and they're associated with things that might either drive the animal away. So you might have higher costs associated with, freeways or whatnot, or things that would entice the animal. And those costs might have to be experimented with, and you could see if you could find, maybe you had some actual evidence, like you captured an animal and put a GPS collar on it and found out where it was going, and then see if you could model it and see how well that particular model did compared to reality. So yes, costs can be lots of different things, but you need to decide on what you're talking about and make sure that all of the layers that you're turning into cost are in the same units. They're all either dollars or effort, like time, or they're just in some desirability, some capability, suitability. How desirable is it for this animal to traverse a certain path? So that's what you're trying to do. You're trying to come up with a friction surface. You can also make it so that you cannot pass through a certain cell. If you either make it no data, which means you can't pass through that cell, or you could code it as a ridiculously high value that would never occur. So like right now, what the border wall, right, is in the news, right? So I don't know if we could do this, but let's say we were going to be somewhere in Mexico and we wanted to get to Albuquerque and we wanted to walk or wanted to find the fastest way. Well, we could make all the roads, lower cost, and then we could make a raster where, if it was flat, open space, it was easy to get through, and then we could code whatever places of the border wall existed as a really high value, and then we could combine all the costs into a single data set. Often that's done just through adding. So you take cost A, cost B, cost C, cost D, you add them all together using raster calculator, and then you have to choose your source, and then you choose your destination, and you run the algorithm, and it will find the least cost path from whatever location in Mexico to a location in New Mexico, and it will tell you what if you've put in some good information, it'll tell you what the best place is to cross the border.
So, Dr. Ray, those are the straight line distance from point A to point B, point A to source. Whatever direction it's coming from, you want to get a cost analysis to get from all those locations back to the source, to give you a number to say why you did this. That's how you.
Yeah, so the straight line distance is the Euclidean distance, and so if you made a cost surface where every cell had the same value, it would actually just find the Euclidean distance. But if your cost surface has other values that represent higher costs, then you're going to get a path that is not a straight line through the path. We should probably show some examples of this. I've got a few more slides that kind of talk about how this works. But maybe I'll show an example and then talk about these. But I'll just show this example, and then I'll do an example in ArcGIS with the Laguna Beach data that we have. So here is an area, and we might be trying to come up with a way to, we might be trying to come up with a road between this point and this point. We want to make a road between these 2 points. So the first thing that we need to do is to run, the first thing we need to do is establish what the costs are. Okay. So most of the costs that we're going to talk about here, we're going to simplify them down into 2 different things. It's going to cost a lot of money to build a road in high slope areas, and it's going to cost a lot of money to build a road through different land uses. In other words, if the land is already occupied, it's going to cost more to acquire. If the land is forested, it's going to cost us a little bit more to chop things down. So we combine these 2 layers and we come up with a total cost. This is a cost in dollars of building a road through every cell. All right, once we have that, we can create this layer. This layer represents where every cell represents the cost to travel back to the source. This is the source. We want to try to build a road from here to here. There's a lake right here. So that's actually a barrier in the cost analysis. So we can't travel through the lake. Right? It's probably, there's an existing road right here. So the cost to traverse that existing road is probably really low. That's ideally the way we should model that. And then this is the cost to direction raster that gets outputted. And then finally, we can use that. See, we've created this least cost path, and what it does is, here's the source, and it follows the existing road for a good bit, and then it breaks off, and it follows this path, because there's not much slope changes, to the destination. So if we want to build a road from here to here, the best way to do it is to use this existing road and then traverse across this area to get to that new destination. So let's do that in ArcGIS Pro. That's not what I meant to do. I'm just going to use the Laguna Beach data you already have. And we can do something really similar to what we already did. What I just showed you, but maybe stepping through it will make a little bit more sense. I'm going to just make a blank project. I'm going to call this Essay Week 4 Class. I probably should have just opened up one of the other projects that had that data already loaded. If I go to catalog, where is that data anyway? I forget. I'm going to add a new map. I've had that data before. Oops. Oh, that's not the same stuff. S. Which lab was that? I thought I showed it in week 1. Yeah. I'm just looking for Laguna Beach. You know what? I bet you it's really smart now. Let's see if I can just go Laguna. Okay. I don't know where I put week 1 data. Maybe it's just right in C10. Nope. Okay. Oh. You're spending forever trying to find it. Laguna Beach data. Open. All right, so there it is. Projects. Open. Anyway, here I got it. C. I'm just gonna put it in C10. It'll be there. Paste. Okay, so we've got our old friend, the Laguna Beach data. The lab's going to use different data. All right, so I'm just going to add. I'll add the C temp Laguna Beach. Should be there now. Oh, hit refresh. There we go. Laguna Beach, and I'm going to add the land cover, and I'm going to add the elevation data sets, just those two. So what we want to do is let's find a path for traversing. So one thing that we could do is, why is this taking so long? Now it's not even opening. That's the smaller of the two data sets, too. Okay. All right, so we've got these two data sets, elevation and land cover. We want to create that same model that, that I just showed you on the screen, except for with different data. So we need to decide what the costs are going to be, what they're going to represent. So right now we have elevation. We have land cover. So we could do something simple and say that we've got developed, we've got crops, we've got 4 different types of developed, we've got crops, we've got some grasslands and crops, and then we've got wetlands, emergent wetlands, shrub, mixed forest. So we can decide the cost for acquiring these different types of of land. We want to build a new path. And again, this is like just an academic exercise, but I think what we should do personally is we should say, okay, well, in our scenario, the cost to acquire any of the developed land is going to be pretty high, and the cost to acquire the other land is going to be low, but it's going to cost a little bit more to actually clear forests and wetlands and make them suitable for putting a road. So those are going to cost more. Forests and wetlands, deciduous forests, any kind of forest. Let's just say these four, they have a cost of, let's just say 10, okay? So any developed one has a cost of 10. Any of the open categories, the crops or the grasslands, they're going to get a cost of 2, and then all of the other ones are going to get a cost of 5. So all these forested types and the wetland types. So how could I create a new raster data set where I now have those categories, 10, 2, and 5? So maybe they're the cost in thousands of dollars. Or Laguna Beach, that's not even, that'd be like millions of dollars. Reassign the values, yeah. I don't know what y'all said on the coast, but you probably said the same thing. All right. So we need to reassign those values. We can do that in either time. Let's start doing just the geoprocessing options. So we're going to do a reclassify is the name of the tool. All right, so I've got my data set. Here's my land cover. It does allow me to actually choose the class. So here I can say, okay, because this is in the attribute table, it's all really dealing with numbers, but because this is in the attribute table here, I can reassign these values over into new numbers. Now these represent numbers. The things in the words in this column represent actual numbers. So if I want to change all these to 10, I just type in 10 a bunch of times. These are all going to be 10. Cultivated crops, it's going to be 2. That's what I said, right? So that's the cheapest. In California, they love to get rid of all the crop areas. When I was a kid, I lived like in the middle of orange groves. By the time I left, there were orange groves and strawberries were everywhere. By the time I left, it was all housing developments. There weren't any orange groves or some avocado groves still up by the mountains. All right, deciduous forests, I said 5 on all these. Just doing this. Scrub shrub. Yeah, it's a type of, it's probably more scrub shrub than anything, right? Because that's another thing that California has a lot of, especially Southern California. That's why it burns so well. All right, now we can specify the output data set right here. Here's the output data set. I'm going to give this a name that I will enjoy, called land costs.
I have a quick question, Dr. Kramer.
Yeah.
How do you know the cost values you're assigning these things are accurate? Like, is that just from other background research?
Yeah.
And you just got to find it out on your own?
Exactly. You have to come up with that. Sometimes your role will be interdisciplinary. So you're going to be the GIS expert, and you're going to have to get information from other departments in your organization, or branch out beyond your organization and come up with a real number. And so the cost that you come up with totally depends on the scenario that you're trying to come up with. So, like I said, if you're a conservation planner, the cost might be more about it being suitable for habitats for certain creatures to get through. If you're looking to build a new road, you're a city planner or a local government planner, then the cost might be to build, what we're doing here. Of course, the numbers are just made up, but they might be in dollars, or they could be in time. But yeah, they're specific to your particular model. So I'm going to go ahead and run this guy, and when I do, I'll have a new layer, and it'll throw that new layer out there. And now there are only 3 different values on here. But what do the values represent? They don't represent land cover anymore. They represent costs. Exactly. So we also might want to say that it's going to cost us more to build in a high slope area than a low slope area, which is probably true. And so the other thing we could do is to modify elevation. We haven't talked about calculating slope yet. We modify slope. So I'm going to calculate slope. Slope's just another tool. So I'm going to calculate slope on the elevation and just call this slope. The output measurement is going to be degree. The choices are degree and percent rise. Next week we'll talk about that a bit more, but we all know what degrees are, right? Like, crack out your protractor, it's marked in degrees, right? Well, percent rise is just the change in run over, the change in elevation over the distance. So it's rise divided by run. So the highest the percent rise can get to is, well, theoretically, is like a really, really big number, right? Because you could have a change. So slope is always degrees is always going to go from 0 to 90, but percent rise can be a really, really big number because the rise could be like really, huge. Yeah, I don't know what the biggest drop-off sheer cliff on the world is, but whatever it is, let's say it's a 1,000-foot drop. Then in one cell it would be 1,000. The next cell would be 0. So you get 1,000 over whatever the distance between your cells are. Let's say it's 10 feet. Then it'd be 1,000 over 10. That would be the percent rise. You'd actually have to multiply it by 100 to get percent. But it would be a really big number. Degree, I think, makes sense to a lot of people. So let's do degree here. And we'll run that. And once it gets created, didn't we create this last week? Or the week before? Yeah, it looks familiar. So what do the dark areas represent, according to the legend? Yeah, those are the high slope areas. If we wanted to reverse that, we could. All right, so we don't know what it costs to actually travel, to actually build a road in a high slope area or low slope area. Okay, we'd have to ask the road building crews, right? But let's establish that it costs more to build in the high slope areas than low slope areas. And we could say that it costs, let's just say that it costs to build in any area above 45, the cost is going to be like astronomical. We'll say 20, which is twice what it costs to even acquire new land, right? So if it's over 45, we'll say it costs 20, which is twice the cost of acquiring land that's already occupied. All right? then we'll say that we can also do the low end. Okay? If the slope is less than, let's say, 5 degrees, it makes sense to say the cost of building isn't much more than it would be to do the rest of the stuff. So let's just make that 1. All right? And then let's just go every 10 there and find out what we could do. We can still run the reclassify tool to do this, right? Reclassify. We can throw slope over here, and then we can actually hit classify down here, and classify unique values. Let's say that, how many classes do we want? I'll say 5, okay? All right, now we can modify these numbers a little bit, because what did I say, 45 before? So if I make this 45 up to, the highest value is not 90, it's 82.881. And we'll say that was going to be 20, right? And the lowest one was going to go from 0 to, what did I say, 5, I think? 5. And that cost was going to be 1. So now we need to come up with the costs in between. So why don't we just go, can we go every 10? So this will be 5 to 15, 15 to 25, 25 to 35. Well, we'll just make the last one 25 to 45 and make it a little bit higher. Okay. So again, these are made up values. So we'll go 5 to 15. Oh, messed up. 5 to 15. 15 to maybe I'll do every 15 now. 15 to 30. 30 to 45. To 45, that's still a pretty high slope for building the road on. I'm sure there are some roads. In fact, I know of one road in Laguna Beach that feels like it's 30, but it's probably not. But still be pretty high to build roads on, so let's still make that one like 10. 15 to 30, that's a little bit more realistic. So we'll make that 8, and 5 to 15 is going to be 5. Okay. So these are our costs, in thousands of dollars, for building a road on these particular areas. So basically, we're saying that it costs about the same to build on a 5 to 15 degree slope as it does to build on a forested area. They both cost the same. So if you have a high slope forested area, now the cost is 10. Okay. We haven't really created this. So let's call this slope cost. Run it. All right, so there are our costs, our slope costs, and we have our land cost. So now, by the way, these values are, ArcGIS thinks it's smart because we derived that from land cover cost, but it's not that smart. These are still numbers, and we should symbolize them as such. So I want to come in here and just say value. So now we got 2, 5, and 10. All right. And we got 1, 5, 8, 10, and 20. And what we want to do is combine these two costs. And what happens if the land cover costs were in thousands of dollars, but the slope costs were compiled by somebody else, and they were just in regular dollars? When we combine them, could we deal with that? Sure. How would we deal with that? How are we going to combine them right now? They're both in thousands of dollars, so we're just going to add them. We're going to do addition. So we're going to add the slope costs and the land cover costs together. Now, if we did the other way around, then I'm sorry. If these represented costs in real dollars, we could just multiply them by 1,000, or sorry, divide them by 1,000 before we added them up. Okay? They're all just local operations. They're just math operations, and we could deal with that. So we're going to do, we can do plus, or we could do raster calculator. Since we're just adding two data sets, plus is fine. Slope costs, land costs. We're going to call this now, one thing that you have to do before you hit OK is under environments, you're going to have to change the cell size to be the minimum of inputs. If you say the maximum of inputs, you're going to get the land cost cell size. So we need the big cells. So we want to do the small cells. So our costs must also be in 2 foot by 2 foot boxes, which makes a little more sense if they're in thousands of dollars, by the way. Right? Because, I don't know, it seems like that would be true, because like here, a lot that's like even a quarter of an acre would be well over $1 million. All right, so we're going to run this guy. I don't know if the math totally works out there, but.
Can you turn back to parameters?
Oh, sure. Slope cost, land cost, we're just adding them together to get overall cost. What's that? It's really ugly looking. Now, one thing is, this is symbolized using a unique value renderer. That's probably not the best renderer. Why? Does 6 represent twice 3 in this raster set? Or is 6 like a label? What do the values represent here? Cost in dollars, right? Yeah. So 6. This is cost in thousands of dollars. So 6,000 versus 3,000, 7,000. So even though there's only 13 different unique values, that's just an artifact of the way we did the process. Even though there are only 13 unique values, this is still a continuous surface. So it'd be more appropriate to symbolize it as such. So we could go in here and change the symbology. This is just, this is just good cartography. If we change this to be a stretch, and then we could choose a color scheme, maybe just yellow to red or something. You can see the artifact of the land cover data set on it. But right now, the lowest costs are the yellows, and it goes up through the reds. Okay, so we've got our cost layer. The values in this layer represent the cost to traverse that cell. If we zoom way in, we can see the individual cells and click on this cell. And it says that the cost to traverse that cell is 25. The cost to traverse this cell is 15. All right, so now we want to run our analysis. Unfortunately, I didn't include any source or destination cells. Well, actually, I did include a source, sorry. if we add the data, I think this is, nope, that's not what we want. Let's just make our own source data. All right. So we've done this before. You're gonna, since I don't have data already, you guys, if you're following along, are going to choose areas. I'm just going to choose one area down in this corner and one area up in this corner, just for fun. Okay? That's the way we'll start off. Start here, and if you guys don't choose the exact same pixel as I do, you're going to get a slightly different answer, and that's not a problem. But it's expected, right? So let's do that. So how do we do that? Well, we can go back over here to catalog, and in databases, this is all the files that it's created as we've been processing. We could go in there, right-click, and say that we want to create a new feature class. This is getting back into ArcGIS, GIS 217. So we're going to create a new feature class, and it's a little wizard. We've got to give it a name. Let's call it source. Let's actually change it to point. We're not going to get fancy. It can be a polygon, and that destination can be a polygon. It's just fine. Let's just make it a point though. Then hit next. And then something that's important is that, well, not on this one, sorry. You can just hit next through this. Something that's important here, though, is that it's in the same projection as the raster data. If it's not, it won't work really well. So what I like to do is hit this little drop down here and say import. That way I can choose an existing data set like the data sets that I've already created. So I'll do my overall cost data set. They're all in the same projection. It's in NAD 83 UTM zone 11. Okay. So I'll hit next. And then I'll hit, I don't think there's anything else to change. Yeah. Yep. I'm going to hit finish. Okay, so here's my source data set. Now before I do anything, I'm actually going to copy that data set and paste it there. And then it's going to name it something like source 1 or something, and I'm going to rename it destination. Destination. All right.
Hey, Dr. Ray.
Yeah.
I was at the one where you got the spatial linkage, the WDS18. You switch to database. Where did you go to get that database? I mean,
if you've been following along with me, it's wherever you put the overall cost layer. Wherever you put that is where you need to get it from. Or any of the other inputs. They're all in the same projection. So if you went like this, new feature class, next, right here, when you hit import, my guess is if you go up here and hit databases, you'll see your outputs. You see under project databases?
I can't tell. Go ahead on, Dr. Ray. Go ahead.
Okay. Feel free to ask any question. I'm going to cancel out of here. All right, so I've got my source and I've got my destination data set, but they're empty right now. So if I add them to the view, both of them, then once they're in the view, I can go over to edit and hit create. And then I have to select my destination once, and my destination is going to be way up here at the top of the hill. I'm going to put it outside of these. See the subdivision right here? I'm going to put it right here. Right below this is like a little feature right here. I'm going to put it right there. And then I do that for the destination, for the source. I'm going to put that like just outside of the beach area here on this road. Bam. Okay. You put yours in slightly different just locations, it doesn't matter. If I hit save, then it will save them. So now when I turn off destination, it should turn that off. If I turn off source, it should turn off that one. Just to make sure, I'm going to clear, so under select here, I'm going to clear the selection. Okay, that's troublesome. It didn't seem to save my source. Let me look at that attribute table. Oh, there's nothing in there, so I don't know if I didn't click right or something. I'm going to click it again. That is in source, right? Save. What does this do? Oh, it was there all along. So I messed up. Now I have 2 dots. If any of y'all have 2 dots, you can just go back here and you can select. Using the rectangle, you can select one of your dots. I just hit delete. It removed it. And I'm going to hit save. I don't know why that screen didn't update, but it didn't. Okay. So now I've got my 2 points. Now I can run the cost distance tool. So here's the cost distance tool. So here, the options for my cost distance tool include, I can specify the source data, and I don't actually specify the destination data yet. I only specify the source. So that's the source data set. The cost raster, which one's that going to be? The overall cost is what I called it. Yeah, it's the addition of the 2 costs. Now this is the main output raster, the output distance raster. That's going to tell us the cost distance. So the cost to get back to the source cell from every cell on the map. So if I choose that, I'm going to call it, I'm just going to call this cost distance. I'll just call it cost distance. That's fine. All right, and then this is the backlink raster. I am going to put cost direction there, just for fun, because we're gonna see that. And I'll run this guy. And remember, I told you this algorithm is, I don't want to say it's complex because it's actually not, but it does have a lot of different options to try. The complex part is that it narrows it down faster than trying every single option. Okay. So this is the direction raster. We'll look at that in a second. If I turn that off, this is the cost distance raster. Interestingly, it doesn't look a whole lot different than the Euclidean distance, does it? I mean, there are some differences, but it doesn't look a whole lot different. You see right here where it starts to get cheaper to go this way. See how this cost band is wider right here, and then even wider. Let's look at why that is. Here's the overall cost. Okay, look at, there's a lot of really cheap costs associated with traveling through this actually relatively flat area. See right there, through the canyon. So that was probably what was generating that. All right, now finally, the last step in this process is to run the least cost path. I don't know exactly what it's called. I'm just going to type cost path. Cost path calculates the least cost path. It's called the least cost path, but ArcGIS doesn't call it Okay, so cost path. Cost path will tell us what of all these are the best choice. Now we could, actually with this information, we could actually find the least cost path. So we'd have to go right here, right here. There's the cell that it's in, and that cell is coded blue. So from that cell, to get back using the least cost path route, we go left into this cell. Now that cell is coded light blue, which is number 4, which means lower left. So the least cost path there is to go on the diagonal down this way. Okay, and then from there we know blue already means left. Then we hit another lower left, and a bunch more lower lefts. And finally, no wait, sorry, that's left, then lower lefts, then left, then lower left. So we could follow the path, but that would be really annoying and take a long time, right? So that's what this tool does. This tool runs the cost path analysis and finds that path for you. So I'm going to do that real quick. Zoom back out to here. So here I can specify the destination, and you can have multiple destinations. And so if you have multiple destinations, you'll have multiple paths associated with each of those destinations. And each of those paths will be given this unique ID. So you want it to be a unique ID. That's the only field I have in that data set, so I have to give it that. All right, then your input cost distance raster is the cost distance raster that you just created. And of course it needs the cost backlink raster, which is the cost direction. I call it cost direction, the ESRI calls it backlink. It derives direction from it. And then finally your output raster. Okay? Your output raster, this is just going to be I'm going to call it the least cost path. Let's look at what this one means. So this one says, for each cell within a valid values on the input destination, a least cost path is determined and saved. Each cell of the input destination is treated separately. All right, so what this is saying, this doesn't really matter for us since I did points. If we didn't do points, if we did a polygon, then everything within a polygon that shared the same attribute would be treated as a single area if we chose each zone. If we chose each cell, then when it converted it to a raster, it would find the best path to every single one of those cells. So typically you don't want to choose each cell, but in our case, each cell and each zone mean the same thing. Best single ignores it only chooses the best path to any particular cell that is colored. So even if I put in 5 or 6 destinations, it would tell me the shortest path from this to the cell that was closest. It would ignore all the others. So in our case, it doesn't really matter since there's only one destination. I just wanted to bring that up so that if you ever try this and you do it with multiple destinations, you'll know that with multiple destinations, you should probably choose each zone most times. That's I don't know why that's not the default, but that's not the default. But that's the one that makes the most sense to me, meaning that an entire zone is treated as a particular destination. And everything that's coded the same number is treated as a single destination. But again, it doesn't really matter here. So I'm going to run this guy. And when I do that, it looks as if nothing has changed, right? I don't know if you saw there for a flash for a second, but you could see it. Actually, I can see it now. I don't know if you could see it. See it now? Yeah.
Shows up better on top of the cost distance.
the cost oh yeah, it's going to show up really well on that one. You're right, I turned that one off. And it'll make a little bit of sense there too. Oh, and what I was saying before, yeah, so there is the least cost path back or forward. It doesn't really matter. In this way, it's either direction. And so, maybe another thing that would help is if we changed the color to like black, so you could see it through everything. Oh, it's actually this one. All right. And then finally, let's say you did this for a really large area, you couldn't even see it at all. It might be good to convert the path to a line. You could go raster to, sorry, it actually was already there. Oh, there's actually a tool called cost path as polyline. It actually recalculates everything and outputs a polyline. This is a relatively new tool. I didn't know it existed. But this outputs a line instead of outputting a raster data set. That's cool. Well, if that didn't exist, then what I used to do, before I even knew that existed, was to do, raster to polyline, exactly. Raster to polyline allows you to take that raster data set, and I'll just call this, path, or LCP, for least cost path. Did raster to polygon, didn't I? Raster to polyline is what I meant to do. Raster to polyline. If you do raster to polygon, it'll try to convert it to a polygon. Right. Field, the value's fine. And then I'll call this LCP. Now the background value matters here. What is the background value here? I'm going to click it and see what it is. The background value is no data, so we should make sure we click no data. Some cases when you want to convert raster to polygon, your background value is 0, sometimes it's no data. Simplify polylines is going to make it so that the line is more smooth. I'm going to run it twice and show you what I mean. So here I chose to simplify the polygons. See how I kind of like split the difference there? I don't know which one is better. I'll call this not smooth and run it again. What's that? It makes it a lot smaller on disk to smooth it out, but it's a question as to how precise not only do you think the data should be, but that the data actually is. Like, it's probably, we did 2-foot intervals. The data is probably not even that precise to begin with. The raster cells are 2 foot, so it's probably just fine to use the smooth point. But the whole advantage of creating the line is that now we can make it look, however we wanted, and increase its thickness. Because before we couldn't do that, so we can increase the thickness. That's right here, right? Yeah. We can increase the thickness and make it dark red. So that's the reason that you might want to do it. I'll turn that other wire off, just so that you could actually make it visually impactful. When it's a raster, you can't do that. All right. the lab actually walks you through doing it as a raster function chain. What we just did as a raster function chain. This time I did test it. You can do everything as a raster function chain. However, there's one kind of, I have it work just fine in the lab, but there's one kind of caveat, and that is you can't do any raster to vector conversion as a, you can't do any raster to vector conversion in the raster function chains. Can't do it. And so you have to specify your source and your destinations as rasters. And so you have to convert your data over into a raster, because it's more common to build your source and destination as vectors. You have to convert them over to raster. And the raster actually has to have the same extent and cell size as the inputs. Otherwise, you're going to get this really weird, like if you made this your source and this your destination, well, first of all, if you just had a little teeny raster right here and a little teeny raster right here, it wouldn't even make it a cost distance. Then it might also just try to use the extent between the two rasters, which in this case would work fine. But what if one was right here and one was right here? Then it would choose a path right through the middle always, even if it was cheaper to go like this. So, what time is it? 2:32. Yeah, that's 4:05. Okay. So actually, to show you what I mean, let's just do it with this data. So in my lab, I give you a source and a destination that's already a raster. But let's just say we wanted to do least cost path modeling totally in raster. Well, to do that, we would need to convert our source and our destination points into a raster that was of the same size as our other data sets. So to do that, you would go the opposite way. You would say feature to raster. That's right there. All right. So I'm going to do a source first, and I'll call this source underscore raster. Okay. Now I can change the cell size right here, but that's not going to do the extent and everything. How do I change the extent and all that other stuff? Yes, environments. So if I go up here to environments, and I have to change all of these things. Every single one of these things you have to change in order to get a raster that's the right size. You have to change the coordinate system, and I'm going to choose I'm going to go way back down. I'm going to choose elevation because that's the original data set that we calculated everything from. So I'm going to choose elevation, and I'm going to choose I'm going to choose elevation for all of these. So the extent will also be elevation. The snap raster will be elevation. And finally, the cell size will be elevation. So if I do that for every single one of these, when I hit run, it will turn the source point into a raster, but the raster will be as big as it needs to be for the data set to work. See, if I zoom way down in here, there it is. See that? That's the source raster point. Now, how do I know the rest of this is no data? I don't know for sure, but I can change the symbology and see if I'll change no data to this yucca yellow. Yep. So now I can zoom back out and I verified. That's good. I want it to look like that. Take note. I'm going to change it back, but now I know that it was the proper extent. It has to be the proper extent or it won't work when you run it through the raster function. So the lab has already created that for you. I was just telling you in the future, if you ran it and you were like, how come I never get it to work? Okay. So one more time, if I do that to the destination, where is destination? Oh, no, sorry, I meant feature to raster. Feature to raster. Okay, this time I'm going to input my destination. Object ID is fine. The output raster, I'm going to call this dest raster. And once I do that, once I do that, I go into environments, and I just change everything. And I want to make them all the same. Why wouldn't I? They all need to be elevation. Not that one, sorry. That's elevation, snap raster, elevation, and cell size, elevation. Same as layer elevation. Okay, now I run that, and I should have one little guy up here in the corner. Let's see. I don't know where it is. Okay. I'm going to zoom in. Yep. See, it put it right there. So that's my destination. Okay. And just to prove that this works, I'm going to do my raster function. The name of the raster function, you can actually skip the cost. It'll compute it all together. So I'm just going to type in distance, and I'll get all the distance functions. So here's all the distance functions. As a raster function chain, they actually run independent of each other. And so cost distance is what you run to get the cost distance. But if you run least cost path, it doesn't actually ask for cost distance and cost direction. Yeah, cost, it's called the cost allocation. That's what it is. It doesn't ask cost backlink. Cost distance and cost backlink. It doesn't require those as part of the least cost path. It actually just asks for your source and your destination. We'll click it. It's still doing it in the background. See here what it asks for? It asks for the source raster and the destination raster, and then it asks for the cost raster. That's not the cost distance raster. That's the cost raster. What's the difference between those two? Yes, the cost distance is based on cost and what else? There's another input to cost distance. Yes, the source. In our case, it's a point. So this is asking for the cost raster. So it's still calculating cost distance in the background, but it actually doesn't show it to you. So here, if we chose the destination raster, and if we go up here, we need to choose the source raster too. Source raster, and we chose for the cost raster now we need to actually choose cost overall cost. Thank you. And again, it doesn't really matter here which one we choose. I'm just going to choose each zone because that's probably the one you're going to choose most often. And now I'll hit create new layer, and it still has to calculate it like it did before, but it should calculate the exact same path. There it is, right there. Is that the same path? That's the one it just calculated. Let's turn this on and off. Yep, see, it covers it up perfectly. That's the same path. So it did it the same way. Now this layer right here is just a virtual layer in memory. What's kind of annoying is that this tool takes a little while to run, right? So if you go ahead and save ArcGIS, you close it down, and you open it again, like after it opens, everything's frozen. It's not telling you why it's frozen. It's recalculating this path for you because it's a virtual layer. And it didn't save that file out. So there are a few tools, raster functions that are like that take a little while to run. They're not just like lickety split, doing a local operation. And so when you reopen, they take a little while to rerun. But there are some advantages to doing it. All right. In fact, that's really those advantages are one of the main focuses of the lab exercise. So we'll get to that when we go back to the lab. So let's see if we've covered all this, and we may be fine. I'll be able to take a break pretty soon. So we talked about